Okay, good morning everyone. So welcome all of you in our first panel, today's first panel session. And our first speaker is Lokesh Singh. He has done his PhD from IIT Kanpur under Professor Bahuguna. Currently, he is doing postdoc in University of Rijeka, Croatia. And today he is going to talk on shadowing type of result for differential equation. So welcome, Lokesh. Please take over.
Thank you to the organizers of this conference for providing me this opportunity to speak in front of all of you. Today, title of my talk is Shadowing as Result for Given Equations. This work is done in collaboration with Professor Lokesh from Brazil, Mr. Dao from Croatia, and so as the title suggests, this talk is based on difference equations. And the other thing is it gives the result a shadowing type result for the difference equations. So to explain what shadowing type result is, let me pose one question first. Okay, so given an approximate solution of some difference equation, can one construct an exact solution? The first part, and not just any exact solution, but the exact solution should be close to our given approximate solution. So if such a thing happens, that means if a given approximate solution of some difference equation if we can construct and if we can always construct an exact solution in the vicinity of the approximate solution, then we say that the difference equation satisfies shadowing property. Shadowing property, also known as shadowing lemma, has a very rich history. There are multiple ways, multiple methods to prove the shadowing property for the difference as well as differential equations. And one of the main method is to assume the asymptotic properties of the difference equations and then using those asymptotic properties to establish the shadowing lemma or shadowing property. So, for instance, exponential dichotomy is one of the main tools to establish this shadowing property. What important part in my talk is that we do not assume any kind of asymptotic properties to establish this shadowing lemma. In fact, we will prove that in our setup, exponential dichotomy becomes a special case, and we also provide examples where there are like where the difference equation does not satisfy exponential dichotomy, yet they comes under our result. So let me begin with my setup. So let us consider a difference equation in a 1/2 space X, and the difference equation is given by the equation for 1. Here the linear maps ANs are bounded and invertible maps. So given this difference equation, we we can find the associated discrete evaluation family. It is given by discrete operator and there are two parameters only. The parameters m and n belongs to the integer set, and for n greater than n, it is defined as a composition of n minus 1 up to n. When m is equals to n, this is identity map, and when n is less than n, it is the composition of the inverse maps.
Just one second. Equation 1 is what is the difference between given actions or what is given action? Ans are given, right?
Ans are given.
Then what is to be found?
So, like given, so if we start with one point, say initial point, and then find the sequence.
Just evaluation,
Continuous evaluation.
Make changes.
Yeah.
So x naught is given.
X naught, like we need to assume some initial conditions. So one initial condition, and then may not be x naught because we are looking the z.
Some sort of iteration kind of.
Yeah, some kind of situation.
One point iteration.
Yeah.
So
With this discrete evaluation family, next we assume, next we consider bounded linear maps PNs on the Banach space X. And using these PN maps and the discrete evaluation family, we define another two parameter operator, G, and it is given for n greater than equals to n as a composition of evaluation family with the linear bounded maps PNs. And for n less than n, it is a composition of evaluation family on identity minus PN maps with the negative sign. So note that this script operator G is important in our case because all of the assumptions are in terms of this operator. So let us consider the semilinear difference equation now. Here this equation is obtained as a perturbation of our linear equation, and these perturbation terms fn's, these are the ellipsis continuous maps with the ellipsis constant cns. Therefore, this function fn, these functions fn's, they satisfy this condition 5, which is ellipsis condition for every integer n and for every x and y in the Banach space.
So actually, this is a linear difference equation because
Yeah.
when we do it, evaluated the previous step.
So
this is called explicit. I mean, the language of explicit difference scheme because information knowing from the previous step you are doing. So it is in that sense it is not semilinear. The linear. In that sense.
Okay. So I because of this these fn's can be moved in your term. So that's why I put there. So our shadowing result is given for this equation. So basically, what we do is we assume an approximate solution for this difference equation, and then under some conditions we provide an exact solution of the difference equation, which is close to the given approximate solution. So here is the main result. In equation number 8, we assume that there is a Zn sequence, which is an approximate solution with delta n as the error terms. And with these delta n's and the operator that we define Gn, we have one assumption, equation number 7, that this term should be finite and we denote it with the L. One more assumption is with the ellipsis constants Cn's. The Cn's and the operator G should satisfy this condition 6. Here this term is a constant Q and it should be less than 1. So if we assume these two conditions 6 and 7 with the approximate solution, then we give then we construct an exact solution.
Just to clarify, what do you mean by exact solution of the difference equation?
So basically, you put the x and it will satisfy the equation number 4 by putting the terms.
So equation. So relations.
No, but the linear operators are given.
You are applying.
Yeah. So if you
evaluations essentially.
Yeah, they will satisfy the evaluations.
So what about sequence action?
Yeah, this is a sequence action.
That is we call it as exact solution.
This is the exact solution. So the last one is not coming. So basically, we give the existence of the exact solution xn, and this xn is in the ball of radius n over 1 minus q around z.
Well, then in that sense, the semilinear is meaningful because we take the respect to x and x. So
So this is our result. Next, I give the sketch of the proof. Here we define an operator T on the space of bounded sequences, and under our assumption 6 and 7, we prove that this operator is well defined and a contraction map. And using the contraction mapping theorem, we obtain the unique fixed point of the operator, and then we define a new sequence as the sum of two sequences. One is the unique fixed point sequence that we obtained earlier, and then the approximate solution that was given. So we define a new sequence xn as a sum of these two sequences, and we prove that this xn is nothing but the exact solution of the difference equation. And by the construction of it, it basically remains in the vicinity of the approximate solution channel. So this is the proof where we did not use any kind of asymptotic properties of the linear part of the difference equation, and then we are able to obtain the Fredholm lemma of the Fredholm property. So as I mentioned earlier, that the exponential dichotomy case becomes a special case in our settings. So next is this result, kind of a smaller result in our article. That first I have to define what exponential dichotomy is. So given a difference equation, here the ANs are again same, the linear bounded and particular maps, and we say that the difference equation satisfies exponential dichotomy if there exist projection maps PNs such that these PNs satisfies these PN commute with the operator ANs. First condition, and the second condition is the evaluation family of this equation AMN, script AMN, satisfies the exponential bounds on the projected spaces by Pn and identity minus Pns. So if such projection maps exist and these two conditions are satisfied, then we say that the equation has exponential dichotomy. So next part is that suppose the equation admits exponential dichotomy, then we show that this setup actually becomes a special case in our setup. So once we assume exponential dichotomy, we have the existence of these projection maps. And if you remember, when we were defining our distinct G operator, we needed bounded linear maps. So these projections becomes the obvious choice for those bounded linear maps. And using these projections PNs, we define our script G operator. Here, these are PNs are projection maps, and identity minus P is again a projection map. One thing to notice, since this equation is satisfying exponential dichotomy, therefore these terms they have exponential bounds. So if we calculate them, we found out that the norm of script G operator is actually less than equals to m raised to minus lambda out of m minus n. So we have a bound for our script G operator in that case. Now again we consider this semilinear difference equation where fn's are ellipsis functions with the ellipsis constant cn's, but this time if we choose our ellipsis constant cn's as a single constant c and the error term delta x as a single constant delta, then we just need to choose our c appropriately so that condition 6 and 7 are satisfied, because here are the conditions 6 and 7 of the theorem. In this, we have taken Cn as constant C and delta x as constant delta, and we have the bound of GMN as a exponential bound. So we can make sure if we choose C smartly, then we can make sure that it is less than 1 and we just make it finite. So these two conditions can be satisfied in this case, and once the condition 6 and 7 are satisfied, we can apply our theorem and we can obtain our result. Okay, so next is first example. In this example, we have
Since you are applying another okay, so on so forth. Fn here you often assuming that ellipsis uniform ellipsis. But that is not really needed. Even local ellipsis you can manage.
Yeah, but I mean, this gives a clear estimate. this gives a clear idea. Otherwise, we can say that that Cn times of this is finite, but since if we can take like single constant, then it gives a clear.
So this problem, this result can be extended to
Yeah.
locally
Locally used. So in the next example, we have so we what we consider is ANs as the isometries of our space X, and in the bounded linear map PNs are such that PNs are uniformly bounded by a constant G, as well as identity minus PNs are uniformly bounded by the constant G. So in these pairings, if we calculate the norm of our extremity of
any family of PN having this problem.
yeah, any family of PN. In fact, we can take B1 and B2 here.
PN equals 0.
That would be like no, but this will give GN of PN will be 0.
The condition of PN is only that uniform boundaries.
Yeah, uniform boundedness, but it should be non-zero. Okay, and I got your point, sir. I got it.
Then I PN equal to I for all. Those conditions will not.
Yeah, if we take P equals to I, then there is a problem because we want this part. We want like this part to be non-condition.
These are the conditions.
These are not conditions, so I can yeah. Okay, I got your point. There should be writing P is non-zero and
I find the bounded sequence of numbers.
yeah, that can.
Condition maybe I think it's general.
Yeah, I will.
Which is essentially trivial.
Thank you. So, yeah. So in that case, we obtain that our script operator G is less than or equals to B, and now the sequence Cn and delta n we just need to choose such that summation of Cn is less than 1 over B and summation of delta n is finite. So if we can make sure that these two conditions are satisfied, then we can apply our this setting.
Maybe
provided sense.
Maybe in your application you may need here is the sequence of finite rank operators which is on the order.
Yeah,
Those
that
cases may be more useful.
Yeah.
This is
This is slightly general. So here is the last example. Here we have considered the difference equation on the product space X cross X, and the operator AN sphere defined as a matrix operator, diagonal matrix operator. The first diagonal entry is defined using a sequence ON, which is ON is greater than or equals to 1. And we define ON upon ON plus 1 into identity. And the other entry is isometric BX. So for these ANs, we can evaluate our associated family, and then for the choice of bounded linear maps PNs, we choose here a constant sequence of bounded linear maps where the first diagonal entry is 0, first diagonal entry is identity, and the others are 0. So in this setup, we calculate our script operator G. It takes the form A15, and like this is the form for when n is greater than or equals to n. There's one matrix, and n is less than n, and there is another matrix. The script operator B. The script operator B is obtained in the same manner as in the script operator A for the linear part of the equation. So now if we calculate the norm in this setting, the norm of the script operator G becomes 2n upon 2m for n greater than or equals to n, and less than n it is ideal, it is 1. But we assume that the 2m's are greater than or equals to 1 for every m. Therefore, we can have a bound of the operator norm of the script operator G, which is on the norm of GMN is less than or equals to rho n. So one thing to note is we got rid of the indices n here. And therefore, if we choose our sequences Cn and delta n such that these two sums are satisfied, these two are the conditions from the 6 and 7. If these two sums are satisfied, then we can make sure that theorem 1 can be applied in this setting as well. So here one thing is that these ONs here put 2-3 conditions. One condition is ON should be greater than or equals to 1, and the other condition is these two sums should be finite. But now, if we choose our ONs such that ON is 1 plus mod n or ON is equals to 1 plus ln of 1 plus mod n, then in these cases, the linear difference equation does not satisfy exponential dichotomy case. So basically, however, for these ONs, our result is still applicable. So, the thing is, this example shows that our result goes beyond the exponential dichotomy. However, as I discussed last night itself, it turns out that if we are taking rho n is equals to 1 plus mod n or 1 plus ln of 1 plus mod n, then it puts extra compulsion on these cn's and delta n minus 1 terms. So this is one thing. But apart from that, we go beyond the exponential dichotomy in these results. These are the few articles that we have used. The first one is the published one from where I have taken this talk. In this article, we have actually covered the continuous part as well as the discrete part. So, differential equations, for the differential equations, we have also given the same result, but I choose to present here discrete part. So, and these are the other differences that we have used. Thank you very much.
Question. See, you need a condition like A and B n equal to P and A.
Yeah.
Do you have any non-trivial examples of P n having this property? But this is some big problem, involving such big problem.
Yeah. So,
is it P n, A, P n, P n's are projections, such that
Projections
P n
are
equal to P n A, which means range of P n's are imaging surfaces.
yeah.
Which is a big problem in eigenvalue problems, right? So, I mean, having non-trivial cases of transferring this complete P n, unless you take spectral projections and all. Taking spectral projections is a big problem, right?
So that is why, like, this is the condition in exponential dichotomy, and that's why it becomes
Do
too
you have
risky.
any example? Non-trivial example of P n? Because the example which you have given there is identity on one corner. No, really.
Okay.
Identity on one corner, 0 and square.
Yeah.
That is fine. The only thing is that
Some
that's
non-trivial
a
example.
trivial. That's a trivial.
Yeah, I understand.
Scalar multiple of identity form.
Yeah. So what I'm saying is that this composition that we are talking about, this the commutativity, this is needed in exponential dichotomy. Yeah. So the thing is, that's why it becomes too restrictive, and we need some general conditions, and that is where our work comes into picture. Because we don't need that condition. No, we don't need that condition. We just needed linear bounded maps only. We don't even need projections. Yeah. So that's why here the thing is. When I showed it,
But you need some condition, something is less than 1.
something is less than 1.
Of course, it will be standard. This thing, there will be stability, so that is okay.
So here, what was
So
I
this
was
is
saying?
exponential dichotomy.
Yeah, this is exponential dichotomy where this commutativity is needed. But in our case, we do not need this commutativity.
Another question is, suppose you want to find the solution of the equation x equal to ax.
Okay.
Then you may have a sequence A which converges to A in some sense.
Yeah.
Then you may have such iterations. So
Yes.
this situation you have any results like that? You didn't do that. A converges to some A. Your interest is to find which point of that A.
Okay.
I
So,
mean,
no, I haven't. No, we haven't yet. But we can consider this. Yeah, we can. Yeah, we can consider this.
So that this technique, if at all,
Yeah.
non-trivial usefulness is there. This can be applied to for solving the operating equations.
Okay.
And then that will be useful. Then you can think of how far this Excel transpose to that, etc.
Yes.
And then in application, you may have only the not exactly this one. You may have that approximate different equation.
Different equation. Thank you.
I read that.
It's a good point. It's a very good. I can. Yeah, we can think of it. Thank you.
Any other questions? Please.
Well, with respect to, let us think the finite difference scheme of a heat equation.
Okay.
This is related to X360.
Yeah, this is
And there is some restrictions, CFL type of conditions that will be more studied.
Yeah.
So if you look at it carefully, similar kind of conditions you are imposing here. It is okay, that will also can be taken care of with the system.
Essentially, you can do the illustrative applications.
Applications with the exact approximate solutions.
What are those aids, etc. in particular examples in the
Okay. Yeah.
No, another thing, if you take implicit scheme, then you can get I minus say A or whatever. Then you take its inverse.
Yeah.
Then
So
it
it
will
becomes
also
invertible.
will satisfy. And this operator has much better property than A itself. I mean, application wise, and
Thank you. So yeah, I will make sure these 2 points.
Any question on online?
No.
Okay, so there is no extra comments. So let's thank Lokesh once again for his nice work.
Thank you.